Before I share myself and what's the main topic, I just give you a live demo. I guess it's always an interesting thing to make this event a little bit entertainment and educational, right? So this is what we do as a company called Timeplus. I'm one of the co-founder. So as you can see, this is the live price for the Bitcoin. I'm not sure whether you are mad for crazy for this stuff, but this is the real thing. If you check your Google, whatever, this is the should be the same price. Even this should be more real time than what you see on the Google. And so essentially, we are building open source and also commercial version of stream processing to handle real time data. And we have all those nice dashboard. We have the SQL-based stuff. So that's why I'm very glad to join this meetup to talk about how we can potentially marry the data streaming with LM, with vector database, with AI. So I go ahead, start the screen sharing. So no matter you love or hug, this is the key thing. And streaming LM, I'm not sure whether that's a keyword you can search, but really want to see what's the potential over there. And I already go over the demo, so you know roughly about what time path is. And I probably will write a blog about what I'm going to talk today, but I guess I can skip this one-on-one because the reason why you are here, because you are either expert or very passionate on this unstructured data and AI and a vector or LM. So I probably don't have to do this a one-on-one talk, but this is my understanding. Again, my domain is really on the data streaming or the real-time side, but my observation as more like a beginner or outsider, that is the trend of AI or the future of AI, at least is really about whether you can get bigger model. But sometimes people are talking about, can we get a smaller model, right? So whether it's LM or SLM, whatever. So it's really, people don't want to take this as a fixed thing. You want to get a much bigger model, have more context, or you can run the model very efficiently on your mobile phone, on your edge devices. So not just on the cloud, but also on the edge, on your smartphone, on your vehicle, on any other stuff. So edge will be very important. Also give you a lot of freedom to access any private data without sending your request or leverage other people's data. And the other thing is really about the real-time part. So again, I have a strong bias on this one, but I think if we can have a better future with the AI to understanding what's going on right now, they can give you a better suggestion, prediction. And one of the example, which is very commonly used in our data streaming space is this. Again, this is a chat app. So you want to understand like, hey, what's my status for my flight to New York? And the robot tell me, sorry, it was delayed for 2 hours. And you ask, can I arrive there, but without the delay too much? And what's the option and the cost? And if this AI is smart enough, they can tell you that is, yeah, you know what, that is, there's an alternative flight with maybe only one seat and only cost you like $1,500. But if you really want to take this chance, you will even have no delay, even sooner, arrive there sooner than expected. Then you make this, come to this hard choice, whether you should pay that extra money or just delay. But again, you see the value that is if the chat robot can access not just the pattern or the LM stuff, but also what's the current pricing, what's the policy, what's the flight status, what's the weather, inventory, your amount of points, all those stuff. So it can give you at least something you can really considering. So it's not generic, it's for you and only valid for the next maybe 5 minutes, even less. So this really will be not just a toy. It can help you to sell more tickets. It can help you to identify some risk, help you to earn some money by trading all the stuff. So that's the point. So I built a demo. Actually, I'm not really building it. I'm leveraged the nice demo from Oli, which is coming from our friend at Biwax. So I'm going to share a little bit about how we can extend that demo to leverage Timeplus and also leverage the vector database. So again, let's show a demo first before I talk about the boring slides. Again, hopefully you are not kind of too surprised for those logos, right? So Hacker News, this is Biwax, Unstructured Data, Hugging Face, Timeplus, and our organizer, Zilliz and Milvus, if you choose. So what I build is a system to load data from Hacker News via Biwax. Then you can do a bunch of unstructured data things. Then again, let's try to see whether we can find any live feed we can talk about. How about, I'm not sure, maybe, again, live demo, anything can go wrong. Anything can go wrong, will go wrong. I guess the best way is to see what data I'm getting right now. So again, I'm using Zilliz, and again, I'm trying to be nice to our organizer, so making sure I use the technology. But the cool thing that is I have a bunch of data over there. If I refresh, it should get some new data if the demo system is still running. Let me see what's the new event recently. Again, there's some F word because Hacker News, right? You know, this there's no rules as long as you are honest. So dog fooding, let me see whether I can search anything dog food. Angry. People usually get angry on the Hacker News. Yeah. So again, this is more like a vector search to see anything you want to ask a question. It's not really answer machine, but try to see whether they match any comment in the database with some a ranking. But what I really want to show that is there should be some recent event. L. This is a new model talk about today, right? So. Yeah. So back to this this demo is so again I talked to every part briefly. So we get data from the Hacker News with their public API. Then this is via the Python code and using Biwax as the framework. And the unstructured data is to, for example, like break the text into smaller text and do some kind of cleanup, and using the Hugging Face to generate the embedding. We can talk about the code later. And the interesting that is the data is keep pushing to Zilliz Cloud via the Kafka Connect. Kafka is a system. So before I talk about that, I'm not sure how you guys familiar with Kafka, because I really want to really share something so that you can some takeaway. So raise your hand if you are okay for me to give you a 101 about Kafka. Okay, cool. So I'm not really wasting your time, which is good. So I skip this part first. Let's talk about Kafka. So you might be very familiar with vector database or LLM or AI. Everyone has its own domain. That's perfectly okay. But I'm coming from the data streaming space. So the reason why there's quite a lot of different players, including Timeplus and the Biwax and other, is it's much better time for us to work on this streaming processing, because it is more common for people to consolidate their real-time data in system like Kafka. And Kafka now is not just about Apache Kafka. It become a protocol just like HTTP, right? For example, no matter whether you are using Chrome browser, Safari, no matter your server is RS, because it's in Microsoft building. Or Apache, you don't really care what kind of browser it is. You don't really care what kind of server it is. As long as they are talking about this HTTP or HTML, it just works. So in the data streaming space, Apache Kafka is the original software, and they built this Kafka API. And now there's a many different Kafka API compatible vendors like Pulsar, like Rapanda, WarpStream, and there are different clients. It can be in different language. So essentially, Kafka have this this key value, and essentially the value can be anything. It's more like a bat array. It can be text for sure. This is very common, but you can even put a bat array, put some image, audio. It's perfect. Okay, it can be just anything, but usually people just put a JSON or arrow or put a buff, and this message is called is put into the Kafka, and as a client, you just talk to one of the server, which they call Bootstrap server, because naturally it is for distributed computing, so there can be a lot of servers, and you as a client you just talk to the first server, which is the Bootstrap server, and helps you understand whether there's other servers in this cluster, and there's an idea about consumer and producer. Producer generate data and put into the Kafka cluster, and the just consume it. But compared to stuff like MQ or message queue, I mean, Kafka is doing this in much more sophisticated way. That is, for example, in the message bus or message queue, you put the data there and you read one message, and other people cannot read it, and all those stuff. But in the case of Kafka, you can read data multiple times, and the multiple clients can read the same data, and it is really designed for scalability. Before this AWS or Azure stuff, Kafka is designed for people to run this in the distributed way in your own local server, assuming anything can go wrong. And anything can go wrong will go wrong. So they have the idea of that about that is you can have multiple servers, and all the data is put into this logic idea about the topic. And the topic can have multiple partition. Partition is a bunch of files. So the idea that is you can put any data into it. You're making sure they will leverage multiple server to save it. Each file is replicated to 2 or 3 times. So it is perfect. Okay, one server goes down because the data can be recovered from other servers, and you can add more topic. You can add any data into it without the limit of the local storage. So there's even idea about this partition and the consumer group. So imagine that is you have 3 servers, and you can in the same time you can have 3 workers to read the data from them, and each one can handle certain workload. So again, Kafka is a very sophisticated system, and now there's a lot of open source or cloud offering. So it is very common for people to put almost anything into Kafka, no matter it's a log, a metrics, your transaction, your video feed, anything can be put into Kafka. You just put and forget. Then you can have other system like Timeplus or some other system to consume it. And also Kafka have an ecosystem. For example, we have a very nice, they call Kafka Connect, which is more like you can read the data from Kafka and send to someone else. So I found there's a very nice connector from the Movers Sync connector. So you can run Kafka and making sure that the data can be put into a different space. So for example, like this is my one of the Kafka clients. I can list my local Kafka. There's a topic called comments. And if I click the comment, you see there's a worker to move data from this topic to the Zilliz cloud. And if I try to preview what is data there, so I just I can set, say for example, I want to check the latest data, and I start to consume it. I should go back to the list. That will be easier, so I don't have to wait for the new data. So you can see there's a, sorry, this is not browser, so maybe the screen is small, but you can see that there's a data keep coming, and every data is a piece of a JSON, right? And the JSON is giving you what's the text, what's the embedding, So that's how, go back to the Zilliz cloud, you can see the number of events. Right now, this is 1693. If I refresh it, it should be a bigger number. Depends on the. Yeah, so for example, this tab is to start the Kafka, right? So I have the Zookeeper, I have the Kafka server, I start a connector, and I also using the open source Timeplus core engine, which is called Proton, to start the server, and this Python script is to keep loading data from Hacker News and generate the embedding and send to the Timeplus database. And the Timeplus, you can directly forward this data to the vector database, but you might also want to do some filtering. For example, someone mentioned F word. You can easily using CQ to detect whether there's any sensitive word or F word. You can do those filtering, or you even only care about a certain topic. So you can easily using CQ to filter those data. Then you can send them to the vector database. So I can hear a little bit about the code. Again, everything will be put in a public repo. To the real time. So as I mentioned, that is there's a multiple components, and the key one is this Python script, and as you can see, that is the main entry is around work data flow for Hacker News, and we leverage Biwax as a very nice framework for you to define multiple steps. So for example, you can define the Hacker News source, which is a very simple way to define, for example, like you can get what's the current ID for the Hacker News, then you can see whether I want to get the recent 150 data, and you can try to figure out what's the Hacker News topic or story, then what is the comment behind it. Then you can download the link, have the full context, and you can break those entire full text to multiple chunk, and you can generate embedding. For example, you can always using OpenAI, but if you don't want to pay the money to the OpenAI, then you can just leverage open source models such as Hugging Face, and it will generate this data like this. So essentially, you have a embedding, which is a very long float array, and you have the text. You cannot control the text on Hacker News, right? So, and Xbox. That's something related, right? So it's not a failed demo, I hope. But again, it's a very easy for you to leverage all those open source tools without paying anything as a SaaS or API. You can just grab what's happening in the social media on your data center and generate the real-time embedding. You can leverage tools like Kafka and Timeplus to do some filtering or even do some kind of transformation. For example, you don't want your credit card or address directly as a text in your vector database. You can easily using CQ to turn those sensitive numbers to some master data. So and lastly, I want to mention that is the reason why we work on this open source project as well as the commercial product is, you may know Snowflake is very successful for sure, but such a OLAP or data warehouse is not designed for streaming or real time. So they are really focusing on how can get massive of data to generate some report or find some type pattern, but it's not really designed for streaming. And Kafka is, again, is a very good technology, and now it's become a new protocol for data streaming. However, it's really focusing on the storage side. You cannot really run SQL on top of it. There's some framework on that to run the computing, but it's not really the core problem Kafka to solve. Kafka is very good for as a message bus, as a buffer, as a storage, but it's not really for computing. And you might know framework like Flink, which is very powerful, very sophisticated, but it's not really a database. So they're focusing a lot on the computing side, but it is rely on Kafka as the storage, or they rely on the OLAP database as the running the ad hoc queries. So the way Timeplus is doing that is we try to provide a new framework of platform for you to easily process data in Kafka or in some REST API, and you don't really need a class of Java servers. You can just run this as simple as a single binary or as a Docker image. You can run the query, you can explore the data in Kafka or in other place. And we have some nice UI and data lineage in our commercial products. And some other stuff I want to mention quickly, that is, you can run streaming processing using SQL without writing any Python or Java code. This is probably text will be too small, but the idea that is you can query what's going on in the live feed. Maybe I can just show the demo, that will be a little bit easier. So for example, if I go to here. Yeah, so this is again the other example, that is you can get the real-time event from GitHub, right? When I run this select star from GitHub, this query never ends. It give you the latest data from GitHub, kind of like animation, but you get the idea that is who are creating new GitHub events, which project gets a lot of star recently. So you can run such a simple SQL to explore data. Then you can do some filtering. For example, type equals maybe say watch event. Right, you can using SQL to easily filter certain data. Then you can run stuff like count. This one. And this will, from now on, keep counting how many events they observe. So actually, you can imagine that is such logic can be expressed using Python, using Java, using .NET, whatever. But SQL is such a common language, and we can just extend that language to help you to process the real-time data. And there's even more advanced stuff like what if the data is out of order, that is this event come first, but some event which should be come early but come late. For example, like you are getting some information from the car, and the car is just went through a tunnel. There's no Wi-Fi or 4G. Then the data arrive late. So all those are funny problem. We can easily express them using SQL. So it's a relatively new technology, but I think if you want to build your product for future, you should pay attention to this new trend. Leverage streaming SQL together with those real-time LLM and vector database to help you build something, as I mentioned earlier, that is very meaningful, very smart, but also understanding what's going on. And there's a lot of use cases. In our case, you can do some trading analysis, figure out whether it's good time or bad time to buy or sell certain stuff. You can figure out whether you are being attacked by someone running a bunch of servers, which IP give you a lot of random requests. So even you can build some real-time machine learning. So the model can keep getting new data and keep training and tune those parameters. So you can have a better result to reflect the recent data trend. So I stop here, and if you have any question, let me know. I'm happy to answer maybe one question here, and then I can answer more questions maybe after all the sessions. Thank you very much. Yeah, go ahead. Yeah, so we work similar as Milvus or Zilliz. That is, we are database, right? So and you can run on your local Mac, on your cloud. So we are not really a data provider. We are happy to connect to any data. For example, for example, like this market data, right? So I have a bunch of data coming from different sources. In this one, for example, I get certain data from, this is CoinDesk, and this is or maybe Bitcoin. So they usually provide stuff like based on WebSockets. So we, as a database, we can easily consume data from WebSockets. Or if you're running your IoT or maybe a fleet, you can having those kind of sensor push data to us. Or you can load data from your database such as Postgres. So that's the technology called CDC. That is, any change you make on the database can generate a CDC message, and this message can be put into us. Then you don't really run your analytics workload on your mission critical database. I mean, all those stuff is running on us. We're more like a mirror, a real-time mirror, and you can understanding all the transaction stuff. So for example, what's the revenue for this hour without slow down your database. Again, yeah, we don't really sell data. We actually is a data tool for you to analyze the data. Yeah. Thanks so much, and happy to answer more questions. I'll be here for the rest of the day. So thanks so much.
Thank you very much for that talk, Jove. Next, we've got Rajat Arya is going to come talk about, this is very short, for your how to handle your data at scale for machine learning. No, model observability. So I'm wrong and not up to date on the talk.
He didn't introduce himself. How many of you don't know who he is? Yeah, so that's Yujian. You should get to know him. He's pretty great. So I'm gonna need your help, everybody. I'm running on just a couple hours of sleep, so I need your energy so that I can get through this. All right, it's the end of the day. Everybody has had a long day, and I'm sure it's really hard to sit in here when the weather is so nice out there. So I'm going to talk fast. We're going to get through this. Can you guys see what I want you to see? I think so. There's a QR code up there. Join our Slack community so you can send me messages and I can reply to them. You can also send me email. I will reply to that too. All right. How's everybody doing? No, really? Come on. Come on, let's go. Come on. I need a little bit more energy. Come on. We just learned how you can find out the price of Bitcoin. I'm not sure what Bitcoin is, but I now can find out the price a lot faster. And I love the idea of having a cache over a streaming data source. That's like, it's a good thing. It's hard to build fan out for streaming stuff. So very cool. Okay. Right, I should tell you about me. So today we're going to talk about visualizing the evolution of ML models. All right, that's what we're going to talk about. I'm Rajat. Hello. I'm a co-founder of a startup in Seattle called ZHub with an X, like Xerox. You're not going to forget that, right? It's ZHub with an X, like Xerox. What is an Xbox? Oh, that's true. It's true. But I think Xerox better captures it because it's the Z sound. For Xbox, you still say the X sound. So we pronounce ZHub with a Z sound like Xerox. But I like that. Please make this interactive because otherwise you're just going to have to keep hearing me. And that's not as much fun as you think. Atul's back there. I used to work with Atul like 20 years ago. He can tell you entirely how boring it is to hear me talk again and again and again. All right. So I'm a software engineer by training. I've primarily worked on large scale systems and distributed systems. I used to work at Microsoft a long time ago. I shipped the first version of OneDrive. Back then we called it SkyDrive, and it was in 2007. And my dev manager was Stephen Bailey, who is still around. I think he's like a corporate VP. He's kind of a big deal, I guess. But I spent a lot of time with AWS after that. I worked on RDS for a while and Elasticache. And I even spent a little time on SNS, which is why I know about fanout and the difficulty of pub sub systems at scale. But for the last 10 plus years now, for over a decade, I've been building systems to support machine learning, starting with an ML startup that spun out of Carnegie Mellon, though it was based in Seattle, called GraphLab, which got renamed to Dado and then got renamed to Turi right before we got acquired by Apple in 2016. Have any of you heard of that? GraphLab, Dado, Turi. All right. Yay. It's not died. All right. Now I need a show of hands from all of you. I need to know more about you. How many folks here are ML engineers? How many people are software engineers? Ah, my people. How many people are data scientists? Okay, okay. Like I feel like I can play one on TV now. How many folks are executives? All right, all right. I think I have to raise my hand too. A co-founder, I guess, yeah. Product design. All right. And who'd I miss? Like, tell me what you're up. Yeah, tell me. Program manager. Yes, technical program manager. Okay, okay. I don't have it up here. I'll allow it. It's another. Okay, makes sense to me. What else? How many folks here are looking for a new role? Cool. I'm not hiring, so you're gonna have to pay attention to my talk instead. But if you are interested in the Seattle tech startup scene, I'd love to talk with you anyway, because there are a lot of really cool startups in Seattle that are hiring, and you should get to know them. All right, that's enough to get started. I want to talk about evolution of models, but I've got to tell you a little bit about ZHub too, right? That's kind of the trade-off. So I'm going to give you one slide. All right, maybe two slides about ZHub, and then we're going to get into the real topic. So our mission at ZHub is to enable robust ML development in every organization. We do this by building ZHub the product, which we consider the modern development platform for machine learning. And who are we? Well, we're a deeply technical team that where many of us have spent over a decade building systems for ML. In fact, we're the team that built the ML platform at Apple. And we started with groups like Face ID, quickly grew out to a whole bunch of other ML teams. We onboarded dozens of teams, shipped hundreds of features on our platform. In 2019, there was 100 features shipped. In 2020, there was 200 features shipped. And we built some pretty big systems. So one of the data systems that we built had over 100 petabytes in it when me and my co-founders left in 2021. And what we got to do working with all these teams and building these systems is really see the pain points of developing machine learning. And I want to clarify what I mean by developing ML, because it relates to the talk as well. A lot of times ML ops talks about deployment and after the model is trained and ready, but there's not a lot of tooling or workflows that support the actual act of building your model. That's what ZHub tries to focus on. That's our area. And we do this, our approach has kind of three parts to it. The first is unified versioning. We scale Git to 100 petabytes per repo. I'll say that again. We scale Git, the normal Git you have, the one on your computer. If you have a Mac, I don't know what Windows ships with. It probably doesn't ship with Git. To 100 petabytes with no limitations on number of files or file size. And what we can do is take immutable snapshots of that repo at each commit using content-defined chunking. And it's a whole other talk to kind of get into how we do our deduplication. But with variable block-based dedupe, we're able to do this really efficiently. And we do it on the edge. We do it on your laptop. So what that means is we don't transfer bytes that haven't changed, and we don't store bytes that haven't changed. The second piece is supporting collaboration, and I think this is often, especially for the folks that have been software engineers at some point in your career, we just kind of take it for granted. We don't remember a world before source control, before the GitHub workflow that exists that we're all used to for the last 15 years. We kind of forget what it's like to try and have a new person join your team, and you can't tell them, oh, just go look at the code reviews from the last month to get a sense of how we build stuff. And you can't use pull requests or code reviews to train new staff members. Well, unfortunately, ML teams don't have that type of tooling today. They can maybe put their code in a Git repo, but they can't put their data there. They can't put their models there. And a lot of these collaboration features of knowing who's working on what, when things changed, how they changed, that's missing. So we're going to talk more about observability today. But that's a key piece of what we do at ZHub. And the third piece is you have to think about scale and performance. And you have to think about this from the edge to the data center and everywhere in between. We have a lot of capabilities to better support this, and we are pretty darn fast. And I'd encourage you to check us out and try us, which is free, by the way. Okay, so today we're going to talk about observability specifically model observability. Now, what do I mean by model observability? What do you guys think? Come on, it's the end of the day. Go ahead, Yujian. Oh, okay. That's a fashion model? Okay. I was like, man, how many LLMs are out there? They're just naming them after people now. Goodness gracious. Yeah, no, that's not it at all. What about model metrics? Maybe that's a ML model observability. You know, your accuracy, your F1 score, precision recall. Is that it? Wait, what about model architectures though? Hyperparameters, model design, the features that the model understands or is aware of. Is that model observability? What do you guys think? Yes, no? There's a lot more slides. So if it was yes, then we wouldn't have a lot more to talk about. Say it again. Logging? Yeah, I like logging. That's a good one. But I don't know. That's like there's a lot in there, right? So it's hard to say no to that, but it's also hard to say yes that's sufficient for observability. What about viz though? Model viz, is this observability? I say no. All of these things are useful, but they're insufficient, unfortunately, because they refer to a specific model or a static model. Instead, model observability is understanding the model's evolution. This means understanding how the model has changed with each build, each experiment, or generally over time. Everybody's with me. You're all looking. This is good. I like it. I like it a lot. But before we jump into what this means in practice, let's take a step back and kind of review how we got here. Why do we need model observability? Why do we need to understand the model's evolution? Well, not that long ago, almost all machine learning was done as a scientific endeavor or an academic endeavor. So what did that mean? That meant the data sets never changed. There were golden data sets. Almost all the data was structured. It came from databases, CSV files, spreadsheets. You know, the models were mathematical proofs, many of them hundreds of years old, and quite beautiful proofs. And the code that implemented the models was bespoke, oftentimes implemented into the program directly in C, or maybe in MATLAB, or maybe in R. I mean, in software engineering terms like this, in computer science terms, this is like implementing software writing in assembly, or maybe even in machine language, without any higher level abstraction to separate the model or the implementation of the model from the hardware. And all this was okay though, like this was fine, because the goal was simply to improve one of these static measures. Because you're trying to publish a paper, right? It's academic machine learning. You're trying to move, maybe you're trying to move your accuracy, or you're trying to train a bigger model, or you're trying to get your model trained faster. So this is the past. This is academic ML. But we all know that this isn't how ML is done today. Oh, I should have said something too. I say ML maybe because I'm old, but I put almost all of AI just into ML. It's just ML, but bigger and usually more unstructured. So just replace ML with AI in your head every time I say it, but I'll keep saying ML. In fact, nothing is kind of like academic ML anymore. I'd argue that industry ML is a completely different beast. And industry ML is everywhere. I mean, every team, like I had to put industry twice in the same line. Industry ML is core to innovation in every industry. Making fun of my own slide. Nobody got my joke. It's cool. I get it. It's late. So what does it mean? What does industry ML mean if it's everywhere? Well, first of all, data sets are constantly changing, hourly, real time, maybe in streams. And the other big change is most of your training data is now unstructured data. And you can see this fun plot that shows how unstructured data, the blue part, is growing way faster than the gray part, which is structured. So this is one big difference in industry ML. The next one is the models are growing in size and complexity. And good luck, you can't find any proofs anymore, any like simple mathematical equations to help you understand what the model's doing. And we're on billions of parameters. Wait, what was Llama 3 that came out today? It was it's 400 billion parameters, right? Is that right? Come on, somebody else must have read this. Yeah? Yeah. The internet's never wrong. So the models are getting huge. This is nothing like academic ML. And what else has changed? Well, the code implementing the models, it's not written into your program anymore. In fact, it's its own ecosystem of packages and frameworks. And you're using libraries that implement the models. And I could have put at least 24 more logos on this slide. I just got tired. And every one of these packages is iterating at its own cadence. And so much of ML work today isn't even starting from scratch about training a fresh model. You're starting from an existing model and you're fine tuning it. You're using transfer learning. So your model is just a part of your application as well, but it's not, maybe you're not training it from scratch. So, okay, all this stuff is changing. What else is different? Well, I'd argue there's a whole new piece to industry ML today that we often ignore, which is the application code. It wasn't really there in academic ML, but this is what we spend all our time doing, writing application code that ties all these pieces together, that ties the data, the model, the frameworks, and the rest of your app code into one thing. Now, what's the goal of our industry ML? What's the old goal for academic ML was moving a metric. So you could publish a paper, my plot looks better than yours, I get a PhD, yay. But what's the goal of industry ML? Well, it's not that simple. The goal is to improve your product or your service or your application. So that individual metric is way less important now. It's insufficient. You actually need to have a more holistic understanding of how your application's performing. So that's why you need model observability. Everybody agree so far? We need model observability? Yeah? Yeah? Okay. So let's figure out how to get that. Who wants to do the rest of the presentation? All right. All right. So we need model observability, but what did we say? We said the data sets are changing all the time. So we got to start with the data. Model's only as good as the data it's exposed to. So as your data is evolving, you need to see and understand how that data is evolving. So my recommendation is summarize your data. You can use techniques like a one-pass sketch summary over structured data, or develop a representation that's low cost, meaning not expensive to run, doesn't take a long time, hopefully only one pass through your data. and use that to understand how your data has changed. So what you see in the on the slides here is a one-pass sketch summary over CSV data. And then on the right side, you can see that summary through a diff. So the colors aren't great, but the top half is supposed to be red and the bottom half is supposed to be green. So the red is the previous commit and the green is the new commit. So you're looking at a diff. But instead of looking at a CSV row by row to try and understand what's happened, you're looking at the summary to see what's happened. And this is a way to better understand how your data has evolved without having to do deep analysis. Okay, so we're starting with data. Next, we've got to do some work for the models too. So I might have put down model metrics, but they are good. You need them. You need them in the experimentation and evaluation phase. It's really important to understand how your model is performing using metrics. But it's more important to understand the model behavior. So when you can, try and develop an understanding of how the model behaves. Why does it predict the way it does? So for tree models, as an example, use something like feature importance to understand which features are important to the model's predictions. So what you'll see on the, can you guys see my cursor? Oh yeah, look at that, there's a cursor. So what you see over here is the dtree viz visualization of a decision tree model or a boosted tree model or random forest model, all the tree models. And this is useful because it's showing you, and you can't read it here, but what it shows is all the different features. And this is a churn prediction model. So those unfamiliar with churn prediction is the application or the task of predicting who's going to leave your product or service, who's going to churn away and say goodbye. And so you're trying to predict what are the features of my product or service that if someone changes their usage of the product or service, what feature they end up using or not using that predicts that they're going to leave. So that's churn prediction. So which is why feature importance is important. Knowing which features best predict churn tell you where you should be putting in your effort. And so the thing on the right is taking the same data and plotting it in a way that's a little easier for me to understand that this feature in red is the most important feature to predict customer churn. So far, so good? So we've got a visualization now of our model that helps us understand its behavior. It's a good start. But it's even more important to see how this changes over time as the model evolves. So you've got to be able to compare before and after. So the left side is before, the right side is after. And I can't make this big enough for you to see it. But if you come and look at my laptop later, or you click on any of the links, you can prove this for yourself. The second feature, not the red one, but the first green one, is different between the left side and the right side. In fact, on the left side, I wish I could zoom in. There's probably a way. I don't know how to do that. What's that? Oh, you can read it. Okay, the second, thank you. Okay, I can't, and I'm looking at it right here. The second feature is online security. And it's missing on the right. It's way lower. It's like, oh, wait, that used to be a really strong predictor of churn. What happened? Is this expected? Like why is the model behaving like this now? Well, it turns out the data set changed. Did you notice it from before? We'll go back. I'll show you. So this is the data set on which the model was trained. And what you see here is this is paperless billing, the paperless billing categorical feature. By the way, our one-pass sketch summaries, they'll show you the top items in categorical columns, and they'll show you a histogram for continuous variables. So what it says here is paperless billing is a Boolean, yes, no. Yes, no, Boolean, you guys get it. And in the old model, there were a bunch of people that said no to paperless billing, meaning they wanted a physical bill mailed to them. But in the new version of the data set, There's only yeses. Huh. Well, seeing that, it makes total sense to me why online security is no longer a predictor of churn. Because the only people left in your data set are people that want paperless billing. So it makes sense that they trust online security. All this is good, right? But could we have figured this out without having the data set summary and the model feature importance? This is where model observability comes in. And I know you're saying it, you're all saying it in your head. These are tree models, this is easy. Show me something harder. Well, all this stuff still works, even on deep learning models. So what you see on the left is the model architecture for a pretty basic PyTorch classifier for birds, taking pictures of birds and classifying what type of bird they are using the Caltech birds dataset. Pretty fun project. And I have to admit, I can't write these. Like I said, I can play a data scientist on TV, but I can't train neural networks from scratch. So I had to ask my co-founder Yujian to help me here. So he did. And you can see the difference on the left is the first version of the model, which was giving him 50% accuracy. And so he had to go and spend a little time on it. And the second version of the model, which is on the right, is now at 71% accuracy. And you can see even without zooming in, that the architecture is different. So this is good. Being able to visually compare even complex things like neural networks, it becomes essential for model observability. Oh, by the way, I should mention, transfer learning beat the crap out of these models. So the takeaway being transfer learning is when you take a deep learning model and you shave off the last couple layers, and then you use the vector. Yeah, I mean, but like in an AI world, when you say embedding, everyone's thinking about text, but yes, you take the vector of floats representation that the neural network has of your input a few layers prior to the classification layer, and you use that, which is now just a big set of floats, and you train a model off of that, like a basic tree model or a linear regression model, and that can outperform building your custom neural net. So for this example, my linear regression model using transfer learning, is 92%, 95% accuracy. So again, don't train your own deep learning model unless you really want to. You'll probably do better doing something else. Same is true for foundation model, like even more true. Please don't do that. I mean, unless you have lots of money you want to throw away and give to some cloud provider. Okay. So now we've talked about why you need model observability and how you need it through data and models. But what does it take to make this go? Like, how do you enable this? I'm going to argue that compute is the key ingredient to make this work. For each of the examples I've shown you, compute is involved in generating the summaries, the visualizations, the analyses. To understand the evolution, that compute has to be executed consistently. And to be able to understand how things change, the artifacts of that computation, meaning the summaries, the visualizations, they need to be referenceable or recorded, so that as you're looking at the model or the data over time, you can see what was the summary previously. And you can do those before and after plots, or those types of visualizations. So compute is integral to model observability. Anyone doubt me on this? So far, everyone's with me. Okay, all right. But now we got to go one step further, right? What else can we do once we've integrated compute? What can we do beyond model observability? So we're just talking about models, right? Well, actually, I think we can do more. If we follow the same pattern, integrate compute into the changes in data, models, and code, we can generate meaningful analyses for every asset in our ML project. And I'm using asset like it's a very general term, and I mean it in a general sense. For so many ML projects, it's really hard to understand things by looking at one file. So far I've shown you examples of a CSV file, a decision tree, a neural network. But for so many projects, there isn't just one file you can look at to understand how things are changing. And that's why I'm using the term asset, because it's important that you can extend the pattern that we've covered already, but across your whole project. So you can say, okay, I want to take these 4 files that are all interconnected. There's a dependency between them, and I can do my analysis and record it and preserve it across all those files. So I've got 2 examples here, and I'm going to come back and kind of show you these examples live. I just don't feel like clicking out of PowerPoint because then it like the screen fluctuates and it's kind of lousy. But once and so I'll show you both of these. The one on the left is a custom summarization over over a different data set, over my unstructured data set full of pictures of birds, the Caltech birds data set. And the one on the right is just an accuracy plot, but it's the one I want, and it's written in Plotly because I understand Plotly and I don't understand like 17 other graphing libraries that exist, and I can tune it the way I want. I can I can put the right colors on it, though I don't like the colors that are there. I can zoom in, I can zoom out, I can slice it and dice it, and I know that it'll be preserved with each change to my project. So I'll show you what this means. But when you can add visual context to any ML asset, then you can achieve ML observability. You have a holistic understanding for industry ML. It starts with data and goes to the model, and it requires the understanding of the context between the data, the model, and the code. So what have we covered? I have 5 minutes. It's good because I'm on my summary slide, man. I got one more slide after this. Yeah, look at that. Like I've done this before. Almost. Yes, almost. So what do we cover? Start with the data, summarize it. Got to compare your models through their changes and try your best to understand the behavior of the model. Why is it predicting what it's predicting? You've got to integrate compute and make sure you consistently run it and store artifacts. Hold on, there's a 4th one. Don't take the picture yet. You've got to extend these steps to have observability for all of the assets in your project. Now's the time, because then you only got one more thing to do. Rejoice. So that's it. Again, join our Slack. I can certainly answer some questions. I also will break out a PowerPoint and show you the same plots in the browser running on ZHub, so that you can see that I didn't just doctor screenshots, as not that I know how. Okay, questions? Go ahead. Okay. I'm back. Let's go. Yes, this one or this one? Yes. Okay. I mean, I left, man. What do you want? I left in 2021. I mean, no, I'm just so the question is like, why isn't Apple doing more with AI? Yeah, I mean, I would certainly say where do those companies make their money? No, yeah, I mean, where does AWS make its money? It's through services, right? Where does Microsoft make its money? It's through services. Where does Apple make its money? There you go. So what Apple does put a lot of energy into is making sure that it is years ahead for on-device ML. years and years ahead. That is its differentiated advantage, and I don't think anyone else can catch up to them. Years and years ahead. I mean, they're the largest. They're pushing TSMC to the 4 nanometer chip design. You know, that's the hardware technology group. Johnny Saruji's group at Apple is it's what makes Apple really hard to catch up to. They can keep making mistakes like the autonomous vehicle project and you know, other projects that don't succeed. But I mean, you still don't have something that works as well as your AirPods do. And that's how many years old? You don't have anything that works like Face ID. That came out in 2017. We're 7 years later. Nobody else can do 60 frames per second, 30,000 point 3D mesh on your face. Why? Because Apple had to build a coprocessor specifically for it, custom designed sensors, custom designed camera. Like, those are the types of investments that only Apple can do because it makes the hardware and the software and everything in between. So I think I would look at it this way. I don't think Apple's trying to play in the consumer AI space. Very focused on delivering the best user experiences for their customers. So I think that's the answer. Dictation on your phone is pretty solid on an iPhone, and that's a local model. There's no cloud. Almost all the models, in fact, I don't know of a single model besides Siri on the phone that needs the network. So there's multiple models in the camera pipeline. There's multiple models in almost every piece of Apple because of the neural engine that Apple's now talking a lot about. But yeah, I think the reason is just it's a different focus. It's a different focus area. There's plenty of teams at Apple doing ML and doing AI work. What's that? Yeah, I mean, look at NVIDIA's business model. It's a different business model. They're selling you bigger and bigger things. So yeah. It's yeah. Other questions? That was a fun one. Go ahead. Yeah. Yeah, you can't do it in Git because yeah, I mean, it's a whole other slide deck, but the short answer is you can't actually put binary files into Git because Git keeps it doesn't understand binary files and it has to keep every single copy of every single file in each commit. What we do instead is we keep a pointer file in the repo as a metadata file that's a hash to the contents of that file. But we don't do file-based deduplication. We're not storing that file remotely using a file-based hash. We do block-based deduplication, variable block-based deduplication over the entire repo. And we take those, we build a Merkle tree out of it, and then we do some fun things in how we store the Merkle tree. We store the Merkle tree in the Git repo under the Git notes section of the Git database. It's a part of the work tree you don't normally use in Git. We have to stop. Is that what you're about to tell me? No. All right, so the short answer is, yeah, let's talk some more. But yes, you can absolutely back up your, what's it called? Your M1 to your M3 using ZHub. And it's still going to be the Git process. It's just going to run our extension. So that first thing I showed you, this is the full summary of that CSV. This is the part that we looked at before, where you can see the, where are we? Paperless billing right here. This is the custom view before and after feature importance for customer churn. This is all in repo, just looking at a commit. This is the PyTorch birds classifier project. Now, along with the PyTorch model, you also see the code changes. This is important context to see what else changed besides just the model artifact itself. And all this is in that same commit. And now I said my two custom views. So this is my summary of my birds data set. So I captured the last modified time. Really simple thing here. If this changes, then I know some files changed in my data set. And that's going to be really easy for me to detect. And finally, I wanted my plotly plot for accuracy. And so I built a custom view over what's actually just a pandas data frame that I wrote out, I pickled out to file, so that whenever I make a commit, so my compute is integrated as ZHub Actions, very analogous to GitHub Actions. Continuous integration allows things to be run consistently, repeatedly, and you store the artifact back into the repo. And that's how you can kind of track all these things. So that's everything I showed you in the slides in a real project. Happy to spend more time and talk more about it. Thank you for your patience and your interaction.
So I'm just gonna use this. Wow, more and more people are leaving the room. This is just really, yeah, I hope so. Yes, there's a lot of pizza. So, you know, I do hope that you guys eat the pizza. Has everybody gotten pizza? Everybody's gotten pizza, right? All right. Well, there's definitely enough pizza for you to go take like probably like half a pizza left. So there's a lot of pizza. How many of you guys have seen my talks before? A couple of you? Okay. So here's the good news. A lot of this talk is not a talk I have given before. So you will get some variation in my talks. How many of you guys know what LLMs are? Yes? Oh, great. That's what I want to see. All right. How many of you guys know how to customize LLMs for your own personal use cases? Oh, you do. You do a little bit. She raised her hand. He raised his hand over there. Oh, he raised his hand too. Oh, okay. So a few of you know how to customize your LLMs. Well, you guys can come help me give this talk then. I can just stand here and look pretty. All right, we'll start this talk. So my name is Yujian Tang. I'm currently a senior developer advocate at Zilliz, and I also run the open source software for AI community here in Seattle. My primary goal, I guess, out of running these communities is just to increase adoption for open source software, and particularly in AI. And I will be doing that full time in about a month. So yeah, and that QR code there will take you to my LinkedIn. If you would like to find me on LinkedIn, you can keep up with all the events that I do, all of the different content that I post, and all these kinds of things like that. I'm going to take this time to also give you some background on myself. So I also worked at a big tech company like Rajat did before. I was at one of the other A's in Fang. So I was at Amazon. How many of you guys are at Amazon? 2, 3, 4? Okay, a few people have been at Amazon. What about Microsoft? How many of you guys are Microsoft people? Surprisingly small amount. Okay, wait, what? Those are the only 2 big companies around here. Google? Facebook? What? Startups? Okay, there we go. That's okay. That makes more sense. All right. So yeah, I worked on the AutoML thing at Amazon, and then here I'm gonna put my phone out here so I have an idea of how long I'm taking to do this crap. All right. All right. So let's get into the actual part of this talk. We're gonna start with an introduction onto LLMs. So I'm gonna talk to you a little bit about neural networks and how LLMs have come to be over time, and then we're gonna talk about RAG. Who knows what RAG is? Who's heard of RAG? Most people here have heard of RAG. That's great. Okay, and then we're going to talk about fine-tuning. Who's heard my talks about fine-tuning? Who's heard my comments about fine-tuning yet? No one? Good. All right. What about, and then at the end, we're going to go through some examples. I'm sure many of you have seen my examples. All right, so let's talk about LLMs. So we're going to take a step back. We're going to go all the way back to the 1960s, maybe the 1970s. So we're going to go and we're going to just take a look at the basic neural nets. Okay, who's familiar with neural networks? Right, you guys have taken Introduction to Machine Learning in college or something like that. So this is a basic neural network. Input, some hidden layers, usually multiple hidden layers, and then some sort of output layer, right? So this is all you need to know about basic neural networks. These were created to do basically predictions, classifications, regressions, that kind of stuff. As neural networks evolved, as the field evolved, we started to see neural networks that were created for specific purposes. And so these purposes were like vision and language primarily. And one of the types of neural networks that we saw getting created in the language space was this thing called a recurrent neural network. Who has heard of these? Who's heard of recurrent neural networks? Okay, quite a few of you. So here in this example slide, this shows an unfolded, let's say, node or neuron in one of these recurrent neural networks. So the idea behind the recurrent neural network is that you can keep track of tokens in a sentence, so like words or things like that, by feeding them back into the layer. However, these RNNs come with this issue that they lose context over time. And who's heard of context window? A lot of you guys have probably seen the words context window. It's been very popular with LLMs. So RNNs will lose context over time. They also suffer from the vanishing gradient and exploding gradient problems. I won't go into that today, but I will talk about how we came up with one solution to address the idea of context. And that was the transformer model. And this was really pivotal in basically the whole story of LLMs. And this kind of came out in 2017, 2018. These transformer models came out. And the idea behind the transformer model is that you can encode your input into a set of vectors, a vector, a matrix, whatever, that we call a hidden state that will keep track of not only the current token, but also the context of the entire thing. So now you have positional embeddings as well as contextual embeddings and things like that. So you take your encoder, you encode some sort of input, you turn it into a hidden state, and you feed that into a decoder. And a decoder is basically just something that's going to take a matrix and it's going to maybe add on something like attention. So attention mechanisms, who's heard of the paper Attention is All You Need? Yes. Oh, very popular. Okay, great. You guys are all very well read in ML. That's awesome. So decoders will take that attention, that hidden state, and it'll produce some sort of output. And this is the basic transformer architecture that came out in the late 2010s. And then in the early 2020s, we have GPT. So GPT-3, the GPT series, generative pre-trained transformers, are a decoder-only architecture, and they take your token and your positional embeddings, and they feed it into a decoder, which, as we talked about, has a self-attention, as well as other components to it. And essentially what it will do is it will predict the next set of tokens. It will predict the most likely next token from the set of tokens you already have. So it takes the token and the positional embedding, and in this example of it's the chicken walked across, and then it predicts how it would finish that sentence. And so in this case, it would be the chicken walked across the road. So this is an introduction to LLMs and how they work. And now we're going to get into the customization of these things. So of the two methods that I presented in the beginning to customize LLMs, RAG was the first one and fine-tuning is the second one. So the first one we're going to talk about is RAG. And the idea behind RAG is quite simple. You're going to take your data and you're going to inject it to the LLM via some sort of vector database like Milvus or Zilliz. And the primary use cases for RAG are basically factual recall. How do I use my data with this LLM? How do I make the LLM understand that this is the data that I want it to work with? That's the primary use case for RAG. And this little, diagram, I guess, that I have here shows you how you can build your own RAG application. The first step is at the bottom. You take your data, you embed it via some sort of embedding model, which you can find on Hugging Face or something like that. And then you put that into Milvus. And you can use Proton by Timeplus to stream real data into Milvus. And then once you have that, once you have your data into a vector database, now you can access that data via an LLM. And so when you are using your RAG application, you will send a query to the LLM. The LLM will then say, hey, this is what I'm looking for. This is the question. Now I need to know what to search for. And it will search the vector database via, what it will do, and this does not show this very well, it will embed that search, the text, into an embedding with the same embedding model that you use to embed your data and put into Milvus. And then it will embed that data, search the vector database, and return the data back to you. And typically it will return some sort of text data back to you. So I'll show you what an entry into a vector database looks like, so you can see that in the next slide. And then it will take all of this returned information and it will turn that into a human readable response for you. So here is an example of what vector data looks like. So this is an example from a real application that I used to do a chat towards data science. And the main two things that you need to pay attention to here are the ID and the embedding. These are the two required fields in a vector database entry. And the rest of it is what we call metadata. So the metadata is where you would store your text, your strings that you are going to embed, as well as anything you want to filter on. So for example, the paragraph here would be the embedded sentence maybe, and then the rest of it would be things you could filter on. You could say, I want to only look at articles that have a reading time of less than 10 minutes. Something like that, right? So this is what the entry into a vector database looks like. You have an ID so that you can find specific entries. You have the vector embedding itself so that you can compare different, the semantic meaning behind different entries. And then you have metadata so that you can pass data around and filter on specific data. So let's talk a little bit about semantically similar data, right? So let's see, what is semantic similarity? So what I'm going to do, this is an interactive part of the session. I'm going to ask you to raise your hand for the sentence that is the least like the other sentences. Okay, so first I'm going to read them, and then I'm going to ask you to raise your hand for them. So this is a throwback to Rajat's talk about Apple. Apple made profits of $97 billion in 2023. I like to eat apple pie for profit in 2023. Apple's bottom line increased by record numbers in 2023. Okay, raise your hand if you think the first one is the least like the other two. Apple made profits of $97 billion in 2023. Nobody. Okay, raise your hand for the second one if you think it is least like the other two. I like to eat apple pie for profit in 2023. Most of you. Okay, great. So that means the rest of you think that the third one is most like is least like the other two. But basically what I want to illustrate to you here is that we as humans have an understanding of how these sentences are related. But if you were to use classic search methods, such as keyword search, and you were to look up Apple profit 2023, you would get the first two sentences. Now, semantic similarity allows you to find, oh, hey, you know, bottom line and profit actually mean the same thing. And probably if someone says eating apple pie, that's different than Apple the corporation. So vector databases empower these kinds of things. So this is an example of text. Now let's look at an example of images. This is my favorite artist, Taylor Swift. And we're going to say if you guys can recognize which of these images is the least like the other three, okay? So raise your hand if you think the first one is not Taylor Swift. Dang, everyone always thinks the first one is Taylor Swift. All right. What about the second one? Raise your hand if you think the second one is not Taylor Swift. Okay. Raise your hand if you think the third one is not Taylor Swift. Okay. Okay. What about the fourth one? Raise your hand if you think the fourth one is not Taylor Swift. Okay. So everybody thinks the first and the fourth one are Taylor Swift, right? You guys are about to feel, no, I'm just kidding. The second one is the one that's not Taylor Swift. So, you know, once again, just illustrating here that as people, we can kind of see, you know, hey, the second and the third one do look a little bit different, right? They don't really look too much like your regular idea of what Taylor Swift looks like. But we as people can kind of see the similarity in these images. And this is another example of how vector search similarity kind of works, okay? So now that we've all been a vector database, let's just talk a little bit about RAG again. Let's back up. Let's close this loop back to LLM customization. RAG lets us inject data and via semantic similarity provided by a vector database like Milvus, okay? So that is how you can customize your LLMs with RAG. All right, now let's look at fine tuning. Who's heard of fine tuning? Oh, great. Most of you guys know about fine tuning. All right, so fine tuning is slightly different from RAG, right? It's still something where you're going to put your data in for the LLM to act in a certain manner. The idea behind fine tuning is that you can augment your LLM by training it on your data. And the main uses for this are style transfer and domain specific usage. Who's seen Devin? Devin, the AI. Oh no, wow. Okay. All right. You guys have seen like Copilot, right? In VS Code, Copilot completes. Okay, cool. All right. So this little diagram here just shows you a little bit about how fine tuning would work. So you would take your data and you would put it into the LLM. You would do fine tuning, and then that would produce a new LLM. And then when you are working with that, you would query or interact with the new LLM. So let's look at some examples of fine tuning of how this can work, right? Of what this can do for you. So I thought this example would probably be very relatable for everybody here. Who has written code before? Yeah, most of you have written code before. That's great. So you see, this is an example of Copilot, and this is, an example of how Copilot works. Not every LLM can do this. So this is something that would be fine-tuned. You can fine-tune an LLM to work specifically in the domain of code. Okay, and this is another example of what you can do with fine-tuning. You can do this thing called style transfer. If you want your LLM to produce images, or I guess at this point LLMs also are able to produce images. Really, we should be calling them foundational models, but LLM has just stuck around as a nice acronym. But if you want to produce different images and different styles, that's called style transfer. This is an example of what you can do if you train your model to produce images in a certain style. All right, so now let's talk about a few of the ways you can do fine-tuning. So there's full fine-tuning, in which you fine-tune an entire model, all of it. And that is very expensive and takes a lot of time and a lot of data. And then there's LoRA. And who knows what LoRA stands for? Yes. Okay, I heard many people say this. So low rank adaptations. And LoRA, essentially what you're doing is you're training a small subset of the parameters. And a lot of research was done around this to show that actually training just a small set of the parameters will actually get you a similar result from training the entire set of models. And then there's QLoRA, which is quantized LoRA. Does anyone know what quantization is? Yes, okay. Ben, you look like you want to say something. Right. So if you guys didn't hear, basically quantization is a way that you can compress the amount of data that you're going to be dealing with from 64 to 32 to 16 to 8 to 4-bit integers. Okay. And QLoRA is basically LoRA, but hey, we're going to add quantization to it. And there's been a lot of research done around this that shows this actually also gets you very similar results, which is really weird. But the reason why this works, or let's say one of the reasons why this works, we don't know exactly why this works, but one of the reasons why this works is because the amount of data that you're training on and the amount of parameters in the model, there's a sufficiently large amount of parameters in the model that if you're just changing the last few layers or the ones that are, let's say, the pivotal ones, you'll actually get the same result as if, because a lot of the what are they called, parameters don't actually have too much of an effect on the output. And when you're training, you're not training on a huge amount of data. Typically, not everybody, some people have a huge amount of data, but you're training on an amount of data that is probably less than the total amount of data that the LM was trained on. So it's actually much more efficient and effective to just affect a small amount of the parameters. Okay, so these are some ways that you can do fine-tuning. These are some types of fine-tuning. And then here are some methods for fine-tuning. I actually spent some time thinking about this, and I was like, methods, types, these kind of sound similar to me, but I couldn't think of a better way to name these. So anyway, there is like supervised fine tuning, which is, you guys are familiar with supervised machine learning. Who's familiar with supervised machine learning? Yes. Okay. It's the same thing, right? You're basically just saying, hey, here's the data, here's what I want, the classification, etc. And then we get into RLHF, reinforcement learning with human feedback. And the next three are different ways that we can do RLHF. So part of the assumption behind RLHF is that A, you can model preferences, that's pairs, as point-wise rewards, and B, you can generalize the models that are trained on the point-wise rewards into, models that are trained, yes, that you can generalize the models that are trained on the point-wise rewards, which I feel like probably makes more sense if I say, like, if you train a model on the point-wise rewards, it is still generalizable. But anyway, these are two assumptions that we make when we're doing RLHF. And direct preference optimization is basically saying, hey, we are going to just train on the preferences. And essentially what this does is this kind of relaxes the restrictions around these assumptions. And then identity preference optimization goes and says, instead of the pairwise rewards, we're going to just, instead of the pointwise rewards, we're going to model everything back as pairwise rewards, okay? And then at the end, we have odds ratio preference optimization. And what this does is this actually does a negative penalty on the things that you don't want to see. And so this was interesting because this is like the opposite of the first assumption. And these are just some fine-tuning methods. There's actually a lot more fine-tuning methods. And to be completely honest with you, they're not understood very well. So if you are interested in machine learning research, this is a great place to get into. Okay, so fine-tuning basically lets us train LLMs to operate in certain styles or domains. And now we're going to go through some examples. Who has enjoyed this presentation so far? Only some of you. Okay, that's okay. It's okay, be truthful. So if you have enjoyed this presentation, I'm going to ask you to do me a favor and go and scan this QR code and go to Milvus. This will take you to Milvus. This is the vector database that I work on. And if you give Milvus a star, my boss will be very, very happy. Yes, I see phones out. That's what I'm talking about. Thank you. This is why I do these talks. Actually, this is just to get more stars on my repos. So in the next section, we're going to go through some examples of how you can do some LLM customization via RAG and via and I'm also going to provide a fine-tuning repo for you. So I have a project, or actually I have many projects that are basically RAG without OpenAI. So how many of you guys know LLMs other than OpenAI's GPT? A few of you. Okay. Cool. Yeah. We've heard a lot of comments about Llama 3 today. So hopefully you guys at least know about Llama 3, right? That's from Meta. Yes. Question. What does the compute look like for fine tuning? It is about, I think, about a 200 million parameter data set called Orca Small or something like that. Will take you about, I'm not entirely sure. I think it's 840 gigabit 8100s training for, I want to say 4 to 8 hours. It's going to depend on the model size, and it's going to depend on which model you use. Okay, so here's the weird thing about fine tuning, right? It's actually a lot of places that you can, a lot of platforms that do fine tuning will charge you by the token, but the tokenization of data actually depends on the model itself. So some models will structure tokens as structured numbers as 2 tokens, and some models will structure them as 1. And the cost of doing this is kind of variable dependent on the model that you're fine tuning, as well as the data set that you have to fine tune on. So to answer your question, it's very hard to know. But this is not about fine tuning. This is about RAG. So we'll get to fine tuning in a couple slides, but this one's about RAG. Here's how you can make RAG without OpenAI. This one uses OctoAI. You guys know OctoAI? Who knows OctoAI? Yeah, OctoAI is sponsoring the next hackathon, so I'm very happy with them right now. Yeah, they're going to provide us $50 of LLM credits for the next hackathon. But they're a local Seattle company, and they host a lot of open source LLMs. All right, and then this one is my AI agents cookbooks. So you guys know what AI agents are. I didn't really talk about AI agents, but who knows what they are? Okay, a bunch of you guys have an idea of what AI agents are. Some of you don't. So I'll give you a very brief overview. AI agents are basically just apps that use LLMs to execute other functions. So this is a project repo that you can check out that uses AI agents. I've got a bunch of projects in there that use Llama Index and Milvus. Who knows what Llama Index is, by the way? Oh, just a few of you. Wow. Okay, what about LangChain? Same people. Wow. Okay. Some of you are very plugged into the Gen AI community, I see. All right, so now this one's on fine tuning. This is an open source fine tuning library that you can check out. And you can use this to run fine tuning basically with YAML or Python. And that concludes my talk in about 27 minutes, so not too bad, I think. Let me see. Yes, okay, that concludes my talk. So let me get this back up here. Are there any questions about, yes? About crack? Oh, RAG, okay. I can't help you with the first one. Wow, I love when people answer their own questions. Yes, cost is a great reason. And in fact, in business, costs might be the reason that you would prefer one architecture over another. But another reason might just be speed, latency, right? LLMs are often the bottleneck in performance for a lot of applications, and RAG is no different. If you try it out, you'll see that, hey, sometimes your things, even if they're only like 1,000 tokens, will take a few seconds to run. And that's, when it comes to real time, it's not great. You don't really want to be sitting there waiting for a while. So costs and speed are definitely two major factors there. I would also say, do you remember what the example they gave was in the needle in the haystack problem? Okay. I don't remember the exact needle in the haystack problem, but if I remember correctly, it was not terribly related to the Harry Potter book series. And that may be one reason why it is simple to do. So I will give my personal opinion on this, I guess. As people who run demos, as someone who runs demos, I often choose to run demos that show my points particularly well. I'm not saying that is the case here, but that is a possible case in this particular reason, in this particular development. Now, I won't say that RAG is going to be around forever. I don't know, right? We're very early in the Gen AI revolution, Gen AI, development stage. But I feel like it's probably going to be around for a while, mainly because of cost and speed. Yes, sir. Yes. Yes. You should probably just embed the PDF. I mean, well, okay. So there's it depends, which is a terrible answer, but it will depend on your PDFs and what they're structured like. So for example, if you have a lot of images, you have a lot of text, you have a lot of figures, maybe you want to do something that can extract those out and then embed things separately. But if it's mostly just like a bunch of text, like you can probably just directly embed PDFs. Yeah. I love when the audience talks amongst themselves. Yes, sir. So I would say that is probably not a use case for RAG. That is probably a use case for SQL or time series databases. Talk to Jove about that. I think that should be fine. I don't. It doesn't. I don't see the LLMs have any particular issue around numbers versus words. Yes, they do. Yes, they do. There's a really funny example with mayonnaise about that. I don't know if you guys have seen that, but that was a really good example. All right, so I'm coming up on my 30 minutes here. Oh, okay. We'll take one more question. Oh yeah, yeah, yeah. So you can go look up fireworks, gradient, unsloth. Yeah, there's quite a few. There's also going to be a platform that's going to be charging by GPU hour coming out. You should talk to me about that. That's mine. All right. So I'm up on my 30 minutes, and I would like to let you guys all get to talk to each other and get to know each other, and whatever it is. So I'm gonna loop some slides for. Actually, I don't have any slides to loop. Did you guys all get to scan the slides at the beginning of the talk, at the beginning of the event, like for either posting a job or looking for a job or anything like that? You guys all got to do that? Okay, cool. Then I don't have any slides to loop. Please get to know each other, talk amongst yourselves, have a great conversation like the one they were just having now.